Hi guys, Daniel here, and today we're going to do the AIME I problem number 15 of this year. So, let's first take a look at the problem. David has 4 sticks of different lengths that can be used to form 3 non-congruent convex cyclic quadrilaterals A, B, and C, which can each be inscribed in a circle radius 1. Let phi A denote the acute measure between the angles of quadrilateral A, and let phi B and phi C be defined similarly, such that sine of phi A equals 2/3, and etc., all these other sign relations. Furthermore, all 3 quadrilaterals have the same area K, which can be written in the form m over n, and we want to find m plus n. So, to start off, just looking at the conditions for this problem might seem a little bit strange, because first off, the problem is claiming that there exists 3 non-congruent cyclic quadrilaterals that are made from the same 4 sticks, and they also have the same area. So how can that even be possible? We should probably figure out how to find these quadrilaterals. So let's go ahead and draw one of the quadrilaterals. That is a terrible circle. There we go. Alright, so let's go ahead and draw one quadrilateral. Okay. Let's call the sides A, B, C, and D. So how might we possibly get another quadrilateral with the same sides and the same area, and also inscribed inside the same circle? How is that possible? Well, one idea might be to swap 2 of the sides. For example, if I swapped B and D, then it might turn into something like this. Okay, this color is a little bit too hard to differentiate. Let's go with green. Alright, so if I swapped B and C, now this becomes B and this becomes C, then we see that we get a different quadrilateral. Perhaps we can get all the different quadrilaterals by just switching 2 sides. And indeed, if we switched instead, say, A and B, then we get a 3rd quadrilateral. Actually, let me switch C and D, because that'll be a little bit easier to see. Let's see. Here, and that's a little bit too long. Let's go with here and here. Okay. So here I swapped C and D to get a 3rd quadrilateral. And we can see that these 3 quadrilaterals are all they're all distinct, because if we take a look at their labels of their size, if we go in, for example, clockwise order, the original one goes A, B, C, D, the green one goes A, C, B, D, and the blue one goes A, B, D, C. And no matter how you rotate them, those 3 permutations of A, B, C, D are not going to change. They're always gonna they can't match each other, so these quadrilaterals must all be distinct. And furthermore, we can actually show that these 3 are the only 3 quadrilaterals that we can get, simply by utilizing the fact that the quadrilateral is completely represented by a permutation of A, B, C, and D, such that rotations are going to be the same, and reflections are going to be the same. So if we start out with, for example, if we start out with 24 different permutations of A, B, C, and D, then rotations being the same would take it down to 24 over 4 equals 6, and then reflections being the same would take it down to 6 over 2, which is equal to 3, and we found all 3 right here. So now we have all 3 quadrilaterals A, B, and C inside the circle of radius 1, and now we have this condition that the diagonals, the sign of the diagonals we know. So let's draw the diagonal of quadrilateral A, B, C, D here. And we know that sine of angle A is equal to 2/3. And we also know that sine of angle B and sine of angle C is equal to 3/5 and 6/7 respectively. So the question is now, how do we combine this information in order to solve the problem? Well, let's first take a look at one of the quadrilaterals. One of the quadrilaterals that we get from reflecting. And let's draw the diagonals for that one. Like this. Okay, so now we know that, what do we know? We know that this angle right here is going to be, let's call the second quadrilateral that we make, the green one, B. So that means this is phi sub B. And we also know that this angle right here is going to be phi sub A. And note that it doesn't really matter which one, if we denote the acute or obtuse angle as phi sub A and phi sub B, because sine of an angle is equal to sine of its supplementary angle. So either way, the sine is still going to be the same thing. So I didn't really care about which whether I mark the obtuse or the acute angle in this case. So let's see what we can do now. Okay, so phi sub A is, I don't really see much that we can do there, because it is the angle between the diagonals, and I don't really know much about it right now, but let's just see for now what else we can do. Let's take a look at phi sub B though, because remember that the green quadrilateral we got by reflecting, by swapping B and C, right? So swapping B and C is basically the same thing as reflecting across the perpendicular bisector of this diagonal, right? So that implies that actually this line right here that connects the original vertex with the new vertex is actually parallel to this diagonal right here, because we reflected this original point to the new point with respect to the perpendicular bisector of that diagonal. So since we know that these two are parallel, we see that actually this phi sub B here is actually going to be the same angle as this right here by parallels. And so that means that this angle right here is going to be 180 minus phi sub B, which implies that since this angle is inscribing this arc right here, and it's also part of this cyclic quadrilateral, that this angle right here is going to be phi sub B. So actually this angle is actually the same thing as one of the angles of the original quadrilateral, and that's very nice because it makes it a lot easier for us to work with. Now similarly, we can find that the other angle, phi sub C, is going to be another angle of the quadrilateral, phi sub C. Okay, so now we have these two angles, but we still have to deal with this phi sub A right here. And because the phi sub A doesn't really chase to anything nice on the original quadrilateral other than just the angle between the two diagonals. So how do we take care of this? Well, we still haven't used one condition, which is that, well, we haven't used several conditions. One condition is that sine of phi sub A is equal to 2/3, sine of phi sub B is equal to 3/5, and sine of phi sub C is equal to 6/7, and also that all three quadrilaterals have the same area K. Oh, wait, never mind. The same area K is what we want to find. Let's see. We also haven't used the fact that the circle has radius 1. Those are the two conditions we haven't used yet. So, how might we use these conditions? Well, it's not so clear right now, so let's go ahead and try to calculate the area K in terms of whatever we can, and then see if we can simplify it to use only these 4 conditions. So how might we calculate the area K? Well, we don't know the side lengths A, B, C, and D at all, so using those sides might not be the most wise. We do know the two angles of the quadrilateral as well as the angle between their diagonals. So let's think about how we might calculate the area. Well, if you recall correctly, one way to calculate the area of a cyclic quadrilateral is 1/2 times. I don't think it has to be cyclic. No, it doesn't have to be cyclic. It's just any quadrilateral. But the area of the quadrilateral is 1/2 PQ times sine of phi A, where P and Q are the diagonals. So let's call this P and let's call this Q. So this might remind you some bit of the 1/2 AB sine C formula for the area of a triangle, and indeed, if we let, for example, d equals 0, then we get that triangle area formula back. And the proof of this formula actually is just using the triangle area formula for each of these 4 sections of the quadrilateral and then adding them all together, and then you can factorize. Or at least that's one proof. But now that this formula is actually very nice for us because it uses this phi a that we didn't really know how to work with. But now we have to figure out the lengths of the diagonals. And we don't know the lengths of the sides, although that would be nice if we did, because then we use Ptolemy's theorem, because AC plus BD is equal to PQ, so it'd be nice if we knew the sides, but unfortunately we don't know any of the sides. We only know the angles. So how might we calculate P and Q this way? Well, let's first take a look at one of the triangles ABQ, or the triangle with side lengths AB and Q. We see that Q is the opposite side for the angle Q sub B. So actually, what we can do is we can use law of sines to relate them. And if we try law of sines, then we get that Q over sine of angle QB is equal to, well, do we want to use this angle or this angle? Not really, because then we have to relate it with A or B, and then we don't know A or B, so that'd be kind of bad. But instead we can use extended law of sines and relate it to the circumradius, to R. So actually we get that Q is equal to 2R, well 2R we also know is just equal to 2, right, because R is equal to 1. So that's good, because now we've used one of the 2 conditions that we had to work with. So that means we just know that Q is equal to 2 sine of phi of sub B. And furthermore, we also know that what sine phi of sine of phi sub B is, because, okay, that's just given to us. So this is very good, because now we think that we can solve the problem. In a similar vein, we can find that P is equal to 2 sine of phi sub C. So that implies that this 1/2 PQ sine phi of A is just going to equal 1/2 times, let's see, 2 sine of phi sub B sine of times 2 sine of phi sub C times sine of phi sub A, which is equal to 2 times 2/3 times 3/5 times 6/7, which is equal to 3's cancel out, and we're left with 2 times 2 times 6, which is 24 over 35, which gives us a final answer of 0.59. And we are done. Hi guys, it's Daniel here, and today, as some last minute AIME prep, let's do problem 13 from the 2018 AIME I.